Okay, good afternoon. I was in conversation. It's now 5 minutes past start time, but I'm here. We're going to be getting way down the pathway, hopefully in multi-rate signal processing, and I'll come back and visit this towards the end of today's lecture, but a plan that I had when I gave you the assignment, knowing that the exam was going to be in the intervening period and did not know where I would end up last week, was that I could shift the due date from this Friday off to next Tuesday if I have to, and I'll make a decision on that. So when you thought you needed to turn your paper, and that's why I was kind of jumped on you immediately, it's like, wait a minute, no, we don't, it's not that bad. I'll take any chance I can get to get ahead, but I'm also going to be reasonable because I spent a lot of time grading papers. I basically been in a marathon session here. So you can see that I did get the project number 1 now finalized. I got the zip package that goes with it finalized this morning. We'll take a look at the project here, I guess early on here in the lecture, but then I've also handed back set number 3 and I've handed back the exam. So I have that. I don't want to make a lot of comments about it. I may comment on some things. You can take a look at it though, because I gave you a bunch of numbers and there's a bunch of histograms. We'll look at those as soon as I get done talking at this point. I will spend more time kind of getting you warmed up to the project, which is why I want to have my first little quick tour of it tonight, just so you see what's in store. I give you lots of hints, or I call it comments, on the document, but it's fun and it's not fun. I mean, parts of it are a whole lot of fun, but I can tell you grading it is very tedious, and I know it's going to be tedious to work a couple of the problems. It's just that way. It's kind of that meticulous kind of stuff. But for those of you that haven't spent many years in engineering or any years being an engineer, it is just that way. I mean, you know, going to school is tedious, it's hard, lots of hours spent. There are times in your workday when it's not the most fun day. Other times it is fun, and I still stand by my saying, if you're not having fun at least part of every day, you're not doing the right thing. I mean, it'll be that way. It'll be hard at some times, but I think about other jobs that I would not tolerate, I mean, very well at all, I don't think. So we'll go in and take a look at that. I just thought I'd talk to you a little bit about this company called Ting, because in my neighborhood, I talked about last week how the city is building out the fiber network for the entire city, and I found out a few weeks back that where I live over here just east in the Garden Ranch subdivision, that they've been building it out now for over months, a couple months now, and they're pretty much done. So they've been laying fiber down most recently, and then they've been splicing it. So I worked in optical communications when I first got out of school. I don't think I ever explained this, but I worked on a program called LaserCom, and it was for the Air Force, and it tested at White Sands Missile Range on the desert floor, and then from an aircraft to ground transmission. So I was involved with the front end of that receiver, 1 gigabit per second, free space, optical communications, and this was around 1978, 79 time frame. So it's quite a long time ago. And even today, 1 gigabit per second is pretty good data rate. I realize we can have on the data buses for our laptops and workstations that can stream things at many gigabits per second, but still, if you could have 1 gigabit per second all to yourself on the internet, let's say, you'd probably be pretty happy with that. So it was a fun project to work on, and then right after that, they wanted me to investigate fiber optics because we already had drivers and things and receivers, so I got the opportunity to work in fiber optics for a little while, doing basically a a research and development project. So that means I really didn't have a boss. I just had an objective, and I got to build stuff, and I got to work with laser diodes and a particular type of photodetector called an APD. Does anybody know what an APD is? Want to take a guess? The last two letters are the most, say something. PD would be photodetector, right? So what would the A mean? Especially if you're in devices. What do you think A would mean? It could mean analog, but it means avalanche. The system that we worked on for the Air Force, we were using a photomultiplier tube, which is a pretty kind of an older technology, but the idea with a photomultiplier tube, which has got an acronym too, PMT. The PMT, when one photon hits the electrodes, and it's a vacuum tube also, so it's not a solid-state device, it will cause multiple electrodes to emit, and then further down the chain, the next single photon causes several, then more, then more, then more. So it's an avalanching effect, so you get a lot of gain out of a photomultiplier tube. So the avalanche photodiode works on a similar principle, except it's a semiconductor device. It's biased at a fairly high voltage, and it gives you this avalanching effect. So when a photon hits it, you get a fair amount of photoelectrons generated, and you get the main thing in a photodetector is having a high sensitivity and having a small dark current so that you don't have a background noise level. And dark current is something that I think is talked about in photodetectors of all different types. What is the photodetector doing? And a photodetector produces shot noise just due to the mechanics of the electrons emission. How many of you remember hearing about shot noise somewhere? Just to say it's noise, though, what do you think? Is it good or bad? It's bad, right? So you want to avoid that, but you do have it. So I actually studied some of these things for my master's thesis at Michigan Tech, which is Michigan School of Mining in Upper Michigan. We never had the icebreaker. I'm still thinking I should do an icebreaker, but the icebreaker is where we go around the room and everybody talks about their backgrounds. But I got a chance to be exposed to the project, and then, like I said, eventually ended up in the optical side. So, and I was working with the fibers in the lab and alignments. I did not do any splicing. So yesterday I talked to a splicing crew and saw how they were taking the fiber that they had laid into the ground, and then they have these vaults and pedestals. So pedestal is what comes up out of the ground, and the pedestal is what you see in our neighborhoods now for the cable TV. But the optical pedestal is, I watched what they were doing because I would be walking my dogs. They were in this little trailer that they parked and worked for hours and hours, and then at the end of the day I walked around and I looked inside and I could see them working really hard, and then they moved it out and mounted it in the pedestal. And it looks very much like a wiring harness that you might have seen for telephone company stuff, where a stub comes up and you see these strips where all these twisted pairs are sitting in there. And what do you think of when you see that? To me, well, it might be an amplifier, but you think one of those is my twisted pair if it's the one nearest to your house, and then there's got to be one, for everybody, and maybe some spares in there. And so I asked these guys, so you're breaking out of the fiber individual fibers that are going to be in these pedestals? And he said, yeah, that's exactly what we're doing. We're breaking it out. So there was one in there. They weren't working on the pedestal that's behind my house that they put in, but I'm sure they'll do that eventually. So everybody will have one. So then they'll just run that one last drop of fiber, or maybe it'll go electrical. It'll probably go fiber, and then it will be some converter in the house that'll convert it back to electrical finally. But so I said, are we really paying for this? And I'm just doing this because this is interesting, and as an engineer, you're going to become more interested in the business side of things. no matter what. Some of you will transition to managers. Some of you will just become more interested because you might want to start your own company. So you have to be more savvy on how you can run a business and make a living doing it. And by the way, these fiber splicing guys had their own truck. They worked for Comcast and other companies. And I said, so what got you into this? They said, we wanted to run our own business. We wanted to, there were just two guys, they wanted to have their own business, which some people like that, and some of you will want to do that too. Sound possible? Initially, you feel very nervous, especially about how do I make money and how do I not do frivolous things that make me lose money. But they invested quite a bit of money in their equipment, and they've gone through trainings of various types. I asked a lot of questions because I'm just curious how did they decide to do it. But they said the way the city got into this, though, was they made a deal, and the company's called Ting. And I looked up Ting, and then if you click on here, lo and behold, you see Colorado Springs is one of the cities that they're going to be selling from. But if you click on it right now, they're not doing it yet. In other words, if I put in my address, it just says not available yet, but $89 a month. And I guess the punchline for me, and then I'm going to stop talking about this, is the city wants all of us to be connected to the fiber network so that they can monitor our gas, power, and water. They're going to get rid of the wireless, I suppose, that they have right now. But by hooking us up and by them working together with this company that's going to mostly use it for data and making money, they'll have all of us connected up, which I sort of scratch my head and say, that seems almost like monopolistic somehow or another. This company is already going to be hooked up to your house because the city will be hooked up to do their work. I don't know. We'll see where this goes. It's going to be like 3 or 4 years before it finally starts to roll out 100%. But I just got sidetracked on that earlier today. So now what I'd like to do is I'm going to talk about the project, but before I do that, I'm going to talk about the exam. So the way you can get to the exam, the exam right here with our password is sitting right here. The histograms are sitting right here. And what I started doing weeks ago is I started making a histogram for every assignment. So I have those 3 homework assignments in here, and there's just 4 of these, so it's not very exciting histogram, but I decided to create it just the same. And then what I do, and what I will do at the end of the semester, is I will take all the homework scores and I let bonuses, when they do occur, overflow across the top. So normalize it to 100%. So what I did today is I processed the first 3 homeworks and put them into the histogram. And you can see when I normalize everything, I add up all the points, divide by the total, and then multiply by 100 to get it based on 100%. Make sense? Dumb engineering math, right? But it's stuff that you got to do sometimes. And there's the mean, 92, and standard deviation is 3.18. So you can see it looks like there's a huge gap in here, but this is 87, and that's like 95. So everybody's doing pretty good. And why am I even spending time on this? Well, last week I got a reminder from the ECE department, but I know these things from all my years. A week from this Friday is the last day to drop. So they want to make sure that I can provide as much information to anybody, even though there's only 4 of you. If I was teaching a class of 100, there'd most certainly be somebody in that class of 100 that's not in good shape and probably needs to drop. But I feel like it's my duty to at least go through this and let you know. And I'm not going to ask you to say anything right now, but if you do want to talk to me or Slack message with me about any thoughts you're having, please do so. So to me, I'm happy with that. And it's, if you had one bad homework day, and I think that's probably the reason why we have a deviation, that's where that comes from. But, some things aren't as good. Some people can start off with over 100%, and then they can not get that in the next one. So the exam is a different story, though. The exam scores varied over quite a wide range, almost 50 points, I think. So all the way from 98, which is the high score, up to 49 or something like that, and then a couple in the middle. So that's what makes the average be what it is for just the 4 people. The very standard deviation is 17.4. It's super, super big. But I did this last year. We had things like this happen too on exam 1. I'm concerned, and I can talk about certain problems, but if I go ahead and the pen had a false start there. 15% is what the exam weighs in at, and up over here. Ultimately, the homework's going to be worth 25%. So my problem for trying to do see with the Microsoft browser. So that's 25%. So right now, that's the only data that I have. So I have 25% out of only 3 homework assignments. I have 15% on one of the 2 regular exams. So I will, as the rest of the semester rolls on, I will do what I call a pre-average, just to give some flavor about where we're heading. So right now, what I have to do is I have to take that 15%, and I have to take the 25%, which is only based on 3 homework assignments. I add those numbers together with the weighting of, appropriate weighting, 0.25 times the exam or homework average so far, 0.15 times the exam average. Add those 2 together, but the base is only 0.25 plus 0.15, so that's 0.4, right? 40%. So then I have to divide that by 0.4 so I can get it referenced to 100% again. So that's what this histogram is. This is just a pre-average. So it's based on just trying to work with whatever data I have, but there's a whole lot more swing factors sitting out there that are still hanging empty right now. Is that making sense? The final.
Grade right now without the final or the project.
Yeah, and all the other stuff. But it's the only thing I can do. And what I always tell people, and I'm used to teaching much bigger classes, is I say, you take these numbers, the raw numbers so far, and then you can postulate, I hope to be able to do this on the final, I hope to be able to do this on the project, and then weight them accordingly, and then put them together and see where you come up. That's about the only way I can do it. I mean, I did that sort of thing as a student, and I want people to be able to sit down and do it. And I'm probably just talking too much because you guys are all old students. You've been doing this for a long time. You've probably done this before. If you were a freshman, think back, then it'd be a whole lot different from my experience. I used to teach 2610, and people seemed like such, relatively immature. And then 1 year time, 2 years time, by the time they're seniors, they're just totally different people. As a matter of fact, it's like raising children, I guess. When they're really young, they definitely don't know that much. They mess up. They have fun. When they get older, you generally don't. I don't like to think about what I was doing when I was really young. It's not something that's really fun to think about because generally there was some embarrassing moment involved there, but engineering's the same way. You gradually got conditioned to everything, and I always say, you've changed for your life. You're not really gonna, you've changed, period. You're not probably gonna revert back, or at least if you were immature in some way, you don't want to revert back to that. So any questions just about this fact that's going on in here? Okay, so I'm going to now leave this and just comment on the problems. Which ones gave the most trouble is the ones I'm going to kind of look at a bit. This one gave a fair amount of trouble. I think it was almost, I'd like to think it was too easy and he made it too hard by thinking too much on it. There was evidence, though, from some people that they didn't really even think it just had an impact that was a negative impact. What do I do with this? Whereas one person did exactly what I expected everybody would do. You just see it and do it. So it was similar to the one homework problem where you had a black box system. You're given 3 inputs and 3 outputs. And this problem, I think, is in the book. It was in a DSP book somewhere from some time ago, where you give a setup like this and you say, assume that the system is time invariant, meaning that it's not necessarily linear, or another parallel problem. I'm just mentioning this because suppose I decided to do that one on the final, just for a variety, where you could say we have 3 inputs and outputs. We know the system is linear, but we don't know it's time invariant. What can you say? So in this case, it was the time invariant example, and I'm asking you to find the impulse response. So time invariance just means you can shift anything back and forth, and the input and outputs just track with that. Nothing changes if you shift it forwards or backwards in time, because the system doesn't vary with time. But if you want to think like, I think our brains tend to think better in terms of linearity. We tend to think superposition is where it's at, right? That's so prevalent in our lives, I think. For an action, there's a reaction, like when you're driving your car. If you hit the brakes hard, you're going to feel some pressure on your seatbelt and so on. And if you get hit from the other direction, maybe it'll cancel it out. Probably will, but it'll still cause damage. But time invariance, you just have to think differently. So to get an impulse response, you can't use superposition. So really, your mind should have just said, X3 is an impulse. It just happens to fire at time sample 4, but that's okay. I can back up for time samples and it doesn't change anything. So that's what you were supposed to see. And then in part B, when I made comment about what about linearity, it was sort of like a taunt to just say, well, what about linearity now? What would you say if you really had to make a comment on it? And I think this threw some of you off too. It was like, can you draw any conclusions? Well, when I first looked at this problem ages ago, I said, if it was linear and I wanted to get a delta, what do I have to do? If it was a linear system, I'd have to form some linear combination of those inputs, which would synthesize a delta, right? A delta at 0. So 1 has got a spike of 1 followed by 2, and 2 has got a 0 followed by 2. So the idea was you just look at that and say, okay, if I subtract 2 from 1, I've got an input of delta of n. So then you can run that on the output y1, subtract output y2, and it should be the impulse response. So that's what I did down here. And if you compare it to what we got under the time invariance assumption in Part A, they definitely don't agree. So, but maybe even before you thought about that in Part B, you just say, conclusion, I can't prove that it's linear, right? Because you just don't have enough information. But if you could come up with a counterexample that disproves something, so what I was really hoping for in B is that you would try to come up with a counterexample where it fails. And that was the idea there. I guess you probably don't want to talk about it. You can just think about it, though. You know, have it like, what was I thinking when I wrote the problem? I mean, when I say I, you shouldn't be sitting there saying to yourself, what was I thinking? Because I don't know what was on your mind. All I know is that one person did exactly what I thought would happen, where the others were fairly mumble-jumbled up, like something just didn't hit you right. I don't know. Or maybe you thought you'd come back to the problem. I don't know either. Have you ever taken an exam where you don't find a problem you can get started on until way back? That's the strategy, though, right? You have to do something. Because if you can't get going, can't get some momentum built up, you're never going to get there. If you sit on the page 1, it's not a good sign. Okay, number 2, this was mixed. I guess I really don't know what caused problems on this one, except that the idea was you had to think about redrawing x of n and then thinking of applying the product u of 2 minus n to it. So if this was to be written as x of n plus 1, it shifts to the left by 1. I think most everybody got tuned into that idea. But then the question was, what does this have to do with controlling what I sketch? Well, this is a time reverse step function, so it shuts off when n is greater than 2. So you just end up with a symmetrical sequence centered on 0. I used Maxima just because I've been playing with it. I'm writing some more stuff for it. Since I'm on furlough, I've got some more things I wanted to just put into it. So I just modeled it in Maxima. And it looks like this was scanned on my scanner, so it's 4 megs, so my computer's having a problem. This one was very straightforward to work if you followed my tip of using the classical method, getting the characteristic polynomial, and then plugging in the initial conditions just to get the coefficients. If you were bullheaded and thought you should be using the Z transform, it didn't work because the initial conditions don't apply in the same fashion.
I did use the classical method. I just went from edit the char poly at the top, the divided, and then use classical method below.
But didn't you have Z transforms on your paper?
It was Z to negative 1, but granted, you did that Z would be close to the char as well. And I did the classical method right below.
So you had this sort of stuff in there? Okay. I'll look at it again because I've got it. But I don't think the coefficients were right, though.
Oh, no, it's probably faster than that.
Okay. This one, very good. The convolution, I think everybody got that one right. This one, not so great again. And probably what it was is maybe the reluctance to want to jump in and do an integral. I don't know, but that was the way to do it because doing it in the time domain would be very, very messy. You have sinc functions that are interacting with each other, so that would just be really messy. Why would it be messy? Because you have the magnitude squared, so you have terms kind of floating all over the place, cross terms, I mean, that you have to cope with. So in the frequency domain, though, it's very easy because it's rectangles, and the rectangles, I just did the positive axes and then multiplied by 2 to get the answer. And joules was just a convention, but it's not really, it really doesn't have any units associated with it. And then the second problem on this page was using the Fourier transform tables just to do an inverse Fourier transform. I thought that was the best way to go with it. You could have done it, well, I just thought that was the best way to go because you have that table and then you have superposition that you can use and you can plug into that pretty readily. I wrote it in sync function. That wasn't a requirement. I think the more typical way it was written was the first line there because that followed right out of the tables, which is what I know you were using. A lot of people wrote, I'm using table entry number 8. And that's what I expected. This one, I wanted it to be done, in my mind, using the time shift theorem. That was what it was sort of built around. You could approach it head on, but if you use the time delay theorem, then it works out probably nicer. You could have done it with geometric series, and that's why magnitude of alpha is less than 1. It wouldn't have to be less than 1, but if you wanted to work it as a geometric series, then you would have convergent series and you could subtract one from the other, so that would also work. This was the most convenient way to go, like I said, and I actually plotted it. It's got an interesting spectrum and spectrum magnitude, but it's got humps in it, but it doesn't have sharp nulls in it like a sinc function does, because the sinc functions are blurred together, is what's going on here, is what I kind of get out of it because of what's in the numerator and denominator. That wasn't really the point, but I just wanted to see what the picture of it would look like. This one, as soon as we got here with the Z domain, everything was, by and large, smooth sailing. There were careless errors that were made, but this was smooth sailing from that point forward. And in reality, you first saw this in 2610. I think you do some more of it in 3205. So you've had a lot of exposure to it. And just like I always thought as a student, when I got to use a Laplace transform in circuits class as opposed to doing differential equations, it was so much easier to solve those problems, and that's really what the Z-transform does for you too. It makes it nice and easy. So I'll let you think about it, and if you have questions or stuff, you can just write to me. It's still pretty fresh in my mind because I've been grading this. I graded the homeworks this morning. I graded the exams last night. So what I want to do next is just take a look at the project. And I'm going to start by going down to the very end of the project. There's a lot of parts to it, but they will break down, and you'll, by dividing and conquering, you'll get there. So at the very end, after the references, I have a lot of comments written. So these comments are related to practical matters about how to do things. So one of the things about writing code, and the first problem is you have to test your code. You have to develop confidence that it's working. So what you might do, well, what you can do absolutely is in WX maxima, I wrote a filth function that's exactly what this function is asking you to do. So it's in maxima. And if you ran that, and I think there's a maxima on the internet somewhere where you can connect to it, you would get the exact answer. I also did a test in Mathematica too. So you might be able to use the difference equation solver in Wolfram. My brain's drawing a blank. Pardon me? Yeah, Wolfram Alpha. You might be able to do it there. But write your code out and test it. And you should be able to put in a very simple test. The ones that I ask you to do are built into the help in the sample code. But you could put in a much simpler test, and you could just write something very simple where you know, from a common sense standpoint, it must give me this for an answer. It's like a very simple type of input, and then add in an initial condition or turn off the initial conditions. Do some silly things that allow you to kind of strain things out. You know, the first thing that will happen when you're not familiar with coding in a particular language is you will make coding mistakes, so nothing will work. Once you get it working, though, then you're to the point, well, okay, now I can use a debugger, let's say, and I can actually put something in and see if what's coming out is reasonable. And I'll just say that from a debugger standpoint, I actually like the debugger in VS Code much better than the debugger that's in Jupyter Notebook. So VS Code is Jupyter, but it's a different Jupyter engine, and it uses the VS Code debugger, which is the same debugger type style that you would use for C and C++ and other languages. So I like the way that one works. And if you set up VS Code like I described in one of the assignment sheets, has anybody not used VS Code? Okay. Do you want to know? I can tell you where you can go to get set up. You can go on the internet, obviously, and find it, but I have a document up here. This thing kind of didn't get talked about because we're not using Julia, but it does have a section in it set up and using VS Code. Here it was designed for doing markdown exports and then creating PDFs, but I do take you through the process of getting VS Code set up. So look up VS Code using your browser, get it installed on your machine. Then what you want to make sure to do is you want to make sure you put in Python and put in Jupyter Notebook support. You'll probably get some of these other packages too, or other extensions installed. VS Code calls them extensions. So an extension is what gives VS Code the profile for doing your language or doing your thing. It's becoming a very popular, and it has become. I've been using it for a long time, but it's now microcontroller software tools are in VS Code. Just about any and everything that involves some coding, VS Code is there. So for me, if I wanted to use VS Code, and I'm not going to bring it up right now because my machine is always so sluggish with my video running, I would just bring it up in VS Code, a Jupyter Notebook, like the samples I'm giving you, and they'll open up right in there. And then you can learn how the debugger works. I don't think I put a debugger example in here because I was using it for markdown code. Is what I was doing in here. So I didn't use it exactly for editing. Last year, I would say in the class of 4 people, I would say 50% were using Jupyter Notebook, Jupyter Lab, and the other 50% were probably using VS Code. I've gone back and forth between the two of them. Right now, I'm more on a kick for Jupyter Lab because it was the first thing that worked really, really well. But Microsoft's VS Code implementation works pretty well these days. I still like one over the other. If I'm not doing debugging, I like Jupyter Lab Notebook in the browser much better. If I'm having to do debugging, I will use VS Code. And I did that for the project already because I needed to check something that I said I can get this solved much faster if I just use the debugger. So I'll take you on a trip of that. Probably not tonight, unless I get time during break and can get it brought up. At any rate, these things, these comments carry you through. So problem number 2 is fairly tedious, but I give some good hints, and I also give some things about how I'm expecting you to do it with multi-rate. And we haven't done multi-rate yet, so I'm not really going to dwell on that. On problem number 3, the new problem that I wrote, this is just a piece of sample code that you can use for building the fixed point algorithm. And this is actually in the Jupyter notebook that's already in the zip file. So this is already installed in there. I'm taking away 4. This was a notch filter, but I'm leaving it's right up in here because you have a notch filter when you do the real-time DSP in problem number 5. In problem 5, you're doing 3 different real-time DSP experiments. One with a chirp generator. This is the one that I said will drive your spouse or dogs or something crazy, so you might want to put your headphones on. You're going to make chirping sounds. This is noise and trying to get intelligibility of a speech waveform, and then the third one is speech waveform with a jamming tone, and then using the notch filter to excise the jamming tones out without knowing where they're at. But you're going to implement it with sliders and things, so you'll just be able to, probably you'll spectral analyze it first, and then you'll know about where to put your sliders. So for future reference, if you want to know how the points add up, this just gives you the grading rubric for how I'll be grading it. So I think it's worthwhile to look at it to know where the big bang amounts are if you're running out of time at some point and you know where things add up the most. So I'm just going to go back to the beginning. The first one is encoding, and the idea here is to be able to include initial conditions. So this would solve numerically the problem with the classical solution technique. You'd put in 0 input, and you'd put in some initial states, and this will produce the output that was in that problem.
With the initial condition, is it y or x of -1, -2,
Yeah.
-3? Okay.
Yeah. I think you asked me that over the weekend.
Yeah.
Ma-
Something similar.
Okay. So here's the example, and here's exactly what you're going to run. These are the two. These are in the doc string for this function, because here's the sample function. I just have the place where you have to write code. And a lot of these things will make sense. I'm initializing things and passing in the states into a vector, and then this is where you write your code inside of here. It's not the only way to solve it, but it's just a way to do it, and I'm trying to just sort of hold your hand and lead you down a path that I think will get you there faster. And then I have pictures like this to help you visualize how the states are maintained. And this is exactly how you're going to be calling it for the two parts A and B that you're going to work. This is the passed on Y, this is the passed on X, and that's what you're going to be doing to test it. So YI and XI are what you're filling in. Second problem is a multi-rate problem, which I want to wait till we go over and spend time on that before I'll come back and talk about this one. But this is just building up a little example problem and then following it through in a very detailed fashion. You'll follow it through in terms of mostly the frequency domain, and we'll be looking at the frequency domain as we get into it almost right away today. So the down arrow means downsampling by 4, and the up arrow means upsampling by 4, and then introducing a reconstruction or interpolation filter is what's going on there, and 2 sinusoids go in. The new baby, I guess you'll call it, because it was my pet project that I thought of this summer when I was working with the smoothing filters in my work, that I've used them before, but I never really got so wrapped up into doing a fixed point implementation. And I knew that it was possible, and I just had not sat down to do it. And if you're going to kind of be in the footsteps that I've been in, a systems person stays kind of void of the FPGA developers and doesn't get forced to do the fixed point stuff right away. But the more and more I've worked in it, the more and more I've run into things where the people that write the algorithms don't know enough about DSP, and they're also reluctant to want to understand what the fixed point aspect is. And the fixed point idea is that you don't double precision is just everything you've grown up with in a calculator. But now if you can only work with integers, can you still get by okay? And I had a professor for my master's thesis who thought integers was just fine. He was happy with it. So what was the fundamental thing that you have to do when you start doing just integer math? You still can do addition, multiplication, subtraction, and division, but when you're thinking of integers, you have to be very careful because everything's always going to become an integer at the output. If you divide 5 by 4, you're going to get 0, for example. But if you upscale the integer values to really large numbers, then they're not as sensitive to the division and multiplication things. They're much bigger. So all of the decimal precision that you used to with floats are going to be in these really big fat integers. And just accept the fact that's the way it's going to be. It's like if this was your big integer number, you could think if I put the decimal point way over here to the right, get that right? No, way over here to the left end and make all these others the fractional bits, then it's like floating point. But when you're working just with a pure integer, you have to carry all that stuff around with you because that's where all your precision resides. So there are tools for doing that, and I thought about doing that, but then I said I like that tool a lot, and I investigated it. It's a free Python library, but it kind of hides what's going on behind the scenes. So I decided it might be better, and based on my experiences with the team I was on at work, the one guy that was really the prime mover that I worked with, he just liked integers, period. He didn't really want to think in terms of a tool. He just wanted, I've got this big fat integer and I want to multiply and divide and stuff like that. So the smoothing filter looks like this. It's just simply the filter we're going to start with in the notes. It models in the discrete time domain an RC low-pass filter with a little bit different scaling is the only thing. It's got a 1 minus alpha, and it's got an alpha. So alpha is called the forgetting factor in some of the literature that I've read, and 1 minus alpha is the complement of that. So usually the way it's set up is 1 minus alpha, and this is where I think it's somewhat backwards, but I'm just going to keep the terminology. 1 minus alpha is close to 1. It's like 0.9 something or another, or it might be 0.8. You just keep the same number in this smoothing filter, and you only allow a little small amount of the input influence what's coming out. So alpha is some small value, and it's pretty much just averaging over the distant past a lot. So the 1 minus alpha is really where the forgetting factor ID makes more sense. It's like you don't forget very much, but you eventually move along and you don't remember the past, but you never let the present input count for very much, because if you got a big noise spike or something, you would get lots of fluctuation in the output. So you just kind of keep things really mellowed down with the smoothing action, and the forgetting factor is generally small. So it could be 1 over 16 up to 1 over 2048. I think in my project this summer I was using 1023, or 1024 I mean. What I'm going to have you use is just 32 and 64. And when I worked on a project at Atmill, it was used in some of their ASICs, and they were using things like 16, 32, and 64. They were used in a radio receiver. And Atmill, remember, is your microchip. And I worked down there. But where I've been working at, we needed something large. We needed a massive amount of smoothing, so 1024. And these are called binary fractions. And why are they called binary fractions? It's because they're powers of 2. So 16 is 2 to the 4, 2048 is 2 to the 11th. So what's cool about that is if you have an integer value and you want to divide it by 16, you don't multiply it by 1 over 16, you use a shift, a bit shift. You can do right shift or left shift. So the right shift is what we're talking about when we're thinking division. So if we want to divide by 16, we're going to shift to the right by how many bits? 4 bits, right? 2 times 2 times 2 times 2 is 16. So if you want to upscale without doing any multiplication, you shift it left. So you can go in both directions, whichever way you want to go. And this is what you do in C programming as well. Python has the same syntax. It's really nice, I think, because Python is interpreted. So if you're working on something like this in C, you can do it. If you're doing this in FPGA, I think they have a similar terminology, but Verilog does things a little bit, I think, very similar. I don't know. I've studied it on and off, and I don't have it loaded in my brain right now. But just give you an idea, if I start off with, and this is what we're going to do, we're going to start off with some integers. I'm going to have integers running from 1 to 8 in this case, in my A range. And what NumPy does, if it doesn't see a float in here, and a float would mean if there's a decimal point somewhere, it says this is an integer. And if I look at what that integer is all by itself down below here, I said, what type is it? And if I just define the integer A from A range, and I say, what is the type of that array, D type is known as the data type of a NumPy array, it just tells me it's an int 64. And that's the default integer size in Python. Whereas if it was a float number, an array of floats, it would be float 64. And that's pretty much the way MATLAB worked when you were learning MATLAB a long time ago. MATLAB just gave you that one option. But Python, MATLAB too, but maybe not initially, Python gives you more options with its NumPy library. So I didn't want to use 64s, I wanted to use int32. So what I'm doing up here and what I have in your sample code is if I take any array, whether it be float or integer, I can cast it to an integer. And so what happens when I wrap it with, say, int32 is I'm saying take all the values that are in A and just cast them to integers. And an int32 is a 32-bit signed integer. Remember the difference between signed and unsigned? Usually in an int value in C, it's stored as 2's complement, and you can have it can take positive and negative values. If you put a U in front of it, then you have a uint or an unsigned int. Python supports all of those just like C does. And just out of curiosity, what style did you learn when you took your C programming? Because C has changed and C++ has definitely changed, but what data types did you use in C mostly?
Like float? You're talking like...
Yeah, when you declare something at the top of your program, you say A, you'd say a type and then the variable next to it. So we were using, yeah, initialize it. So it was int.
It was like everything.
It was int, float. Did you do int32s though too?
We did.
And embedded systems, I think we did.
Oh, embedded you would for sure. But what you have to do usually in those other uses of C, you have to import a header file that has those types defined in it, right? Otherwise, you didn't have access. They weren't defined anywhere. The original C just had a few types defined in it, like int, float, uint, and bool for boolean, and so on. But then they came along and they wanted to have more types available, so then they had a header file define more standard types, and then now they're pretty much, I think, if I was learning C, I would look for a book that had all that stuff in it, because learning the older style is just kind of not as good anymore. It's better to be precise. Int, the problem with int way back when was if you were working on a 16-bit computer, it would be an int 16. If it was a 32-bit computer, it would be the largest int it could represent, int 32 and 64 and 128 and so on. But that got to be ambiguous if you wanted to port from one platform to another. So the standards bodies came along and said, we need to be clear on this. So I myself love things like int32. Int is too vague. Int32 tells me it's an integer, which means it's signed, and it has 32 bits in it. So I'm casting it. So every element of this array called A32 will contain 32 bits. So here I just went through a print statement and I stepped through the values, and I'm using something new that I've just learned in the past summer because I've known about it but I've been lazy. I didn't want to learn about it. Something called F strings. It's a relatively new language feature in Python. Print is one of Python's core functions for printing and helping you do low-level debugging. But now you can say the string that's inside of the print is an F-type string. You'll notice in my examples I use R an awful lot. And R is a raw string is what it's called. It's just what other properties does that string have and how does it get acted on. So what I like about F strings, and the reason why they were created, is you wanted to have a string that's formatted rather than doing the old-fashioned formatting, which I'm still a big fan of because I learned it first in C and it follows the same rules that C does. You put the string and then you put symbols in there with a percent sign, like I'm saying percent 4.3F or something like that for float, or 5D for 5 decimal digits, whatever. And then you have all of the variables that are going to get mapped into that string listed at the end. But now with the F string, you can have them on the fly. So with the curly bracket here, I can just say, I want to push in the display of this Python variable A32 at index K, and if I put a colon after it, I can say, oh, by the way, I want it displayed as a decimal value that's got 4 decimal places. And if I wanted to do a float, it would be, 4.1F or something like that. But here I just wanted it to be decimal values. So, and it's right there on the spot. It's going to get formatted into the string, and that's how that string gets created. I think it's pretty cool. It can be used all over the place in Python, and I didn't get as excited about it until I did this summer when I actually had to be doing it a lot. So it's called the F string. Got it? Has anybody ever heard of F strings before that? When I learned Python over 10 years ago, and F strings did not exist. So at any rate, you can just see how the bit shifting is working here. Upshift by 2, downshift by 1. Another thing that can be helpful in debugging your code, or just understand how this filter is going to work, is this binary repr, or binary representation. If you've got a NumPy array and you want to look at one value of that array, I can wrap this function from NumPy around it. Since I've imported all of NumPy, I don't have np.binaryrepr, but I just can type binary repr, and what it will do, it will just list off for all of these 3 values that I'm wanting to look at, the binary representation. And if it's positive number, it's got a bunch of zeros in it. In this case, it's just got a 1 out here at position 4. So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So that's 8. Make sense? And if it's a signed number, then it's going to have all this backfilling of the sign bit, 1 coming all the way down. That's just the 2's complement value. But what I like about this is when you're debugging and wanting to understand what's going on, you can see what bits are active in your array. You know, where's the activity, where's the action at? Because in this implementation, what can happen is if you shift too many bits off, you're going to lose all your precision and you're not going to have something that functions very well. So what I do to implement the filter is I say in this simple algorithm that I'm going to, this is like 1 over 32. That's what alpha is going to be. So that's 5 bits shifted to the right is what I'm going to be doing on that x value. And I want to have 1 minus alpha times y of n minus 1. So how can I simplify the multiplication there? I can just factor out the 1 times y, and then I can subtract a bit shifted version of y because the alpha sits over there. So you see how that's being done right in here. This is the 1 minus alpha, but it's done without any multiplication. And then this is the alpha times x, no multiplication. Is this grabbing you like I don't have to multiply? And why do you not want to multiply? I mean, I'm not a computer architecture person, but isn't multiplying more expensive than adding? So we can get by without any multiplications. So that's the idea here. Now I'll talk about later maybe a DSP slice. Has anybody ever heard of that? Part of the Xilinx, which is now AMD. They have the DSP slice. But at any rate, this is to do this multiply free is what the idea is. So that's the implementation idea. And then I explain it a little bit more down here, where I actually don't even need to upscale and down. I need to downscale, but I won't have to upscale because if I don't upscale, I can just basically avoid. If I'd upscale the input to get larger integers to keep precision, then I'd want to shift b bits away. Let's just keep the value unshifted, and then I'll do some shifting to the right for the 1 minus alpha, and then alpha, or then the old value comes through. So this ends up being my interpretation of the block diagram for doing the multiplierless smoothing filter idea. You'll play with it using L-filter too, but then you'll build this up and see that it works about the same, except it's not going to have the same double precision. It's going to have finite precision, but we can occupy more of the 32 bits in here, and when we push bits off, we're still keeping enough precision to be pretty accurate, and you're going to be evaluating that. So I think probably that's about as far as I should go on this for right now. I'll let you get into it, though. I'm willing to bet that most of you have never thought about this before, though. But have you ever been thought about if you had a tough problem to solve and you weren't allowed to use multiply, like you're a chip designer or an embedded systems developer who didn't have a floating point engine on their microcontroller? How can you do that? I mean, I learned about that a long time ago, but I never confronted it because I just chose microcontrollers like the one you're using, John, in the DSP lab, that there's a float multiply on there. But when I first learned about real-time DSP, people were trying to build things that ran fast and low power consumption for cell phones. So they said, most of our algorithms are running fixed point, all integer multiplication, and that's the kind of stuff that they're really good at. So when I studied this summer, I was trying to explain it to the FPGA person how I wanted to view it, because I didn't want to lose precision. That really what drove me to want to learn this is the fact that I was concerned that they weren't going to be worried enough about precision, And I was a systems person worrying about ramifications of having lack of precision would make matters worse. It's like the fundamental thing was, do I want to do a hack job or do I want to do it right? And a hack job is probably just going to be really embarrassing to the manager. It's like, but you promised me you could do this. Oh, but then the FPGA people wanted to have it in fixed point, and if they did sort of a hack job at it, it's not going to work at all like I expected. And I basically wanted to draw closer to the FPGA people and say, we can do this right, and I think we'll come out successful. Does that sound like a worthy thing? I mean, I think that's what engineering also involves, is teamwork, and say, let's not hack at it. Let's understand what we're doing. It can't be that hard. So you'll have fun with that problem. This is what it's all about. You have a sensor data, and it's the orange line. It might be something on your platform. For me, it was space communications, but it might be something that's in motion. But you have sensors that pick up a lot of noise. So the noise is the blue thing, and you don't want to have the control signal have all this noise on it. So the smoothing filter is going to come along and reduce a lot of that excess noise that's on there. That's the application I was into, at least. So you get a chance to do that. Then I'm giving it some shape, but I just made the shape up. You know, this is purely made up. This line for S, 5,000 plus 0.01 n, 10 cosine 2 pi over 10,000. I just said, what can draw a picture that kind of looks like something that's kind of looks good, right? Because it has the noise, and then if I overfilter, what's going to happen is the filter will not be able to stay with the signal. If the signal's moving too fast, so it won't be able to stay with it anyway. But in my problem this summer, I needed lots of smoothing, but there's platform dynamics in its specifications, and there in fact is a lag, but the lag is acceptable. It was a good trade-off for what I had to do, and I had to demonstrate that to my coworkers that this was an acceptable trade-off for our application, and I actually used the transient response like we were looking at early in the semester with the difference equations and everything. Pretty cool. Other problems we'll get in and look at the real-time DSP. I will definitely demo that in here and let you see how that works, but you got one taste of it weeks and weeks ago, right, with the Pi Audio Helper, and you'll be doing more of that stuff. It works. What's in the zip package on the website. Let's jump over here and just see what that looks like. You got to download this zip package here. That has some sample notebooks. It's got some graphics that show up in the notebooks, which are kind of nice. And then it's got a couple of different audio files. And then to test everything out, this was my audio test vector. It's just because of the size on this WordPress website the university set me up with, I had to break them apart. 8 megs is the largest file I can have on my web server. That's like, I feel like I'm in a straitjacket, but those are their rules that they set up for me. Last project will involve a software-defined radio file, and last year's file took up about 500 meg. And how did I deliver that? Slack, no problem. It'll get to you and you'll have it. And that'll be a cool experience because you'll say, I'm working with a really big set of data, but you know, it's sampling that over a mega sample per second. So, and it's got lots of bits in it. So you get an idea of how does everything work with DSP. We chunk through lots of data in our lives when we listen to internet streaming and video and everything. We all understand that though, right? DSP is where we're actually right on top of it. It's like we really appreciate what the costs are involved. It's not trivial. So pretty much time for the break right now. So I think what I'll do is just we're going to look at this, which is related to a homework problem right after the break. So Does anybody have any questions or want to talk to me now, or we can do it after class too? I'm going to stop the video though and let us have a break. Okay, before we move into the multi-rate, we've got just an example that is almost identical to one of the homework problems, and it's very close to what we were just talking about with the smoothing filter, so I want to spend some time with it. It's basically saying we want to do an impulse invariant design. It's not a super popular type of digital filter implementation, but it dates back probably more from control systems. Control systems, digital controls, they might go for impulse invariant or step invariant, because in controls, step response is so important. So if they're trying to implement some processing in DSP, they might want to patterned after a traditional analog solution. So that's where this kind of comes from, the idea that you could get an RC low-pass filter. So this is right out of the book, and it just says we have the RC low-pass filters A times e to the S naught t, where S naught is a time constant. So if you started in the Laplace domain and you could start this for a higher order system, then you could use the inverse Laplace transform. But here this is so simple, just a single pole. So we can relate it to just an RC low-pass filter. And if it's an RC low-pass filter, then we can also relate it to a 3 dB cutoff frequency, 1 over 2 pi RC. So I don't know about you, but in DSP or in systems modeling, I'm just happy with F3. I don't need to have the circuit elements. If you were going to build this on a breadboard or something, you would care about, you know, the R and C values. Or when I taught that undergraduate, not for majors, electronics class, we needed component values, but F3 is all that matters to me. So if I drop down here now and want to do impulse invariant, all we're going to do, according to the definition, is we're going to just sample the analog impulse response and then put a scale factor of t on there, is what the book talks about. We'll have an alternative means just in a moment here, but so we'll put in the impulse response, and we replace t by nt. So what we see once we do this, we see e to the minus we can take that that e to the minus 2 pi f3t times n, and we can make it look more like what we had at the beginning of the course. So we can make that e to the minus 2 pi f3t be a, and we've studied that a lot already, right? So this is exactly what you would want to do if you'd want to implement an RC low-pass filter in the discrete time domain. You just use that equation, e to the minus 2 pi f3t, or f3 over fs if you wanted to write it that way, because t is just the sample spacing. Then you can relate that to the parameter a in the first order low-pass filter. I've had to do that before, and you can think about that for the project problem if you want to, but it's really depends upon just what you want to accomplish and where you're coming from. If you're working with a legacy system that had analog filters in it, then you'd want to pattern, you know, the digital design after that somehow or another, but eventually you'd just be void of that probably. It might be settling time or something too, might be related to this, and this has got an exponential decay, so maybe that's what's going to drive it. If it's controls, and you're taking controls from Dr. Platt, you've been involved with stuff like that, haven't you? Settling time and rise time. At any rate, though, what is the drawback of this system? So if we implement it that way, we can now z-transform the a to the nu of n, because we've seen that before, and that's what's down here, except we now just have a different scale factor that's into our system because that was just brought down from up here. And then we just have the standard first order model, and we can look at the frequency response of that. So what's going to be done here is just looking at the frequency response for a fixed sampling rate of 10 kilohertz, but then letting the 3 dB frequency range from 0.1 up to 5 kilohertz. And if you want to take this a step further, you can put in a factor of G, where you set up G so that you have unity gain at DC. And that, to me, I put that in the problem because that just makes a whole lot more sense to me. I want it to behave just like an RC low-pass filter would. It'd be unity gain at the low end of frequencies, and then it would start rolling off. So that's like a fudge factor, and there's the fudge factor to match the DC gain to the analog filter. So I modeled this in Python, just wrote 3 different subplots for different cutoff frequencies, and lo and behold, and you'll do something not quite as involved as this in the homework problem, but you get to see that if we're 2 orders of magnitude, our sampling rate is 10 kilohertz versus 0.1, so we'd be 2 orders of magnitude greater. We're kind of okay down in through here, but then you can see that it starts to not follow the RC low-pass filter as well. And if we let the cutoff frequency of our digital filter implementation be even larger, like 1 kilohertz or 5 kilohertz, it's essentially worthless at 5 kilohertz. It's doing almost nothing. This approximation really only works if you're way oversampled. And in the smoothing filter application that you're going to be experimenting with in problem number 3, it's way oversampled. So you get a lot of good filtering action going on in there. And in a digital control application, you'd be able to do that too, because the bandwidth probably isn't that wide of the signal. It's not varying that rapidly. It's like, for me, in certain applications, it might be if the signal strength is going up and down. It's not that volatile. Now, if we were talking about what goes on when you're driving a car around and you're talking about multipath, there the fluctuations are very rapid, and there it's very difficult to deal with that. When I worked in that quite a few years ago for a small company in town, I was likening it to sitting on a Bronco that was bucking away and trying to hold on to it and not getting thrown off. It was like almost impossible. There's so much amplitude fluctuation going on when you're driving at freeway speeds. But if this was used, it would have to be more along the lines of this. I would venture to say that this might not even be good enough. If you look at this, the idea of this plot was to say that when the filter is dropped off naturally to about 30 dB down, it's starting to deviate by a few dB, and then it gets even worse than that. So if that's not acceptable, you'll have to oversample even more in terms of your design. But it just shows you that the impulse invariant is simple. It can work well, but it's costly in terms of the oversampling factor. There's another section in the book it's in the book, but I don't really like talking about it, so I'm going to skip over it. It just says continuous time processing of discrete time signals. Why would anybody want to do that? It's like if we're going to DSP, we're doing it because we want the software flexibility. Why wouldn't I want to come out of a DSP system to do something in the analog domain? Well, the first thing that comes to mind to me might be some time delay or something that you can only do in the analog domain more precisely. And where I have seen this happen is usually not in this scenario, but it might be that you're going to use DSP in a radio receiver to process in an analog automatic gain control amplifier. So you put an A to D converter on a received signal at a receiver, and you take that further downstream and you sense it in the DSP domain, and then you feed back through a D to A converter an analog control signal to control the analog. And maybe yours, Maxim, does that in some of its parts. That still happens, right?
Yeah.
So that's the closest thing I can see. This is just kind of, I think this was a platform to be able to talk about stuff. That's the reason why they put it in here. So example they brought up was a non-integer delay, and I don't like the idea of having to have to do that in the analog domain. I'd rather just say, no, I can do that in the DSP domain. So, but the simple example that I looked at was how I can get a half sample delay. So if I go to Python and if I look at a moving average filter like we looked at a long time ago, and I make it have an odd number of taps, then what that moving average filter is going to do, and that's what this Python example is trying to show you, is that I'm going to get a 2.5 sample delay. And what I'm basing that on is this is the input, and then this is the output out of a m is equal to 5 filter, and it has the peak, which doesn't show up in this particular case where the frequency I'm using would be right here, so that's where the 2.5. If I was processing a lower frequency signal, it would be more obvious, I guess, but nominally that's just saying the peak shifted by 2.5 samples, so I'm getting a half sample delay. A more realistic thing, though, might be what I have over here in the Jupyter notebook. I'm just going to take a quick look at that. There's a half sample delay example I just showed you, but here in the Scikit DSP COM digital COM module, I have a function called time delay, and the time delay function allows you to put in a fixed delay where D is just an integer, and you can just delay using a Lagrange interpolating function that will delay by whatever fraction of a sample you want to. And that's a pretty nice function that's used in various applications. When I say that, it's like if you're thinking in DSP, you're thinking, oh, I can only move by one sample. Not so. I can move by fractions of a sample, very tiny fractions, if I use the right sort of interpolation filter in the discrete time domain, all in the digital domain. So here, I just moved by 1 and 2.1. So you can't really see the way I plotted this, but if I was to look at the zero crossing on here, where I'm connecting the dots, because I'm not using a stem function, I'd see that it is indeed 1.1 samples a delay. There is an inherent issue in using the Lagrange interpolators that you have, because you want to make it a causal filter. You actually have to have some fixed delay just in going through the filter. You get it fixed delayed, and then you can have an interpolation polynomial sitting around it so that it's causal. You see, I'm saying by causal, remember, you wouldn't want to use future values because you can't run it in real time, but that's what goes on here. You end up creating, say, a 10 sample buffer, and then I shift it down to an operating point, and then I can deviate about that. So making that more clear, here's an example where I let D actually be time varying. So it varies over time. It varies from 0 to 5 samples over the length of 50 samples. So here's the plot I get when I just run that through the function. It's in the notes. I'll let you, if you're interested in it. What's a good application for this? Well, you can do pitch shifting. If it's audio, you can shift pitches around by compressing or expanding the time axes. Does that sound believable? Or maybe Has anybody ever done soundstage or heard about how you can make a pitch of one person match a pitch of another singing? I think there's standard algorithms out there now where you can make people sound better than they really are, because you can, and you can do it with, a vocalist. My wife used to like to watch the TV shows, what are the various shows that have been out there, trying to remember the name of it. It's not on right now, but it used to be on. It's on every now and then. Finding a New Singer or something. What's the name of that show?
Where they press the button and they turn around?
Yeah, American Pop, but what's the other one?
American Idol?
American Idol, that type of stuff.
What about America's Got Talent?
Yeah, both of them, all of them actually, where people are singing, where they're singing. Can they sing well without having some auto tune on there? And it's used for special effects in rock music too. And then I was using it in the channel emulator. I was using it in satellite testing, where you can actually feed an RF signal through right at S-band microwave frequency, send it through, and then I can put in a profile that represents the Doppler of a satellite that's moving further away, so I can let the range change between two platforms. It works. It works really nice. That's how I got involved with this, because I was helping a company develop a product that did that stuff. Okay, now into multi-rate sampling. We can come back if we have time tonight and look at what I have implemented in the Jupyter Notebook already, and you may definitely want to take a look at that. So now we're going to move into changing sampling rate, discrete time processing. So we've been sampling analog signals since the beginning of this chapter. We sample at cap t. Suppose we want to sample at t prime. So we might, we're typically going to be looking at making t over t prime be a rational number. And I'll just use one example, and I'm going to write down here. Since you're not old like I am, you can't remember that in 1976 was when the compact disc came out. A long time ago. Seems like forever. But I was excited about it when it came out. I was old enough to definitely appreciate it, and I wanted to experience it. It took a while for that to happen, because they were expensive when they first came out. But at any rate, they chose 44.1 kilohertz as the sampling rate. Why? Well, the story goes that Sony and who's the other company? Sony and Philips, two electronics giants back in that day, and still pretty significant right now. They wanted, somebody at Sony, I think, wanted what Philips and Sony were working on together. They wanted to be able to have the entire Beethoven 5th or the 9th, I don't remember, symphony on a compact disc, played at a tempo that a typical classical music conductor would want to have it recorded at. They wanted that to fit on the compact disc in stereo. So, and they wanted to use 16 bits per sample for left and right channels with some encoding to prevent errors due to the reading off of the compact disc with dust and other dirt on it. So somehow or another they arrived at 44.1, and that is what the standard was when it came out. What has the studio been doing for a long time? They've been working at 48 kilohertz. So can we convert between 44.1 and 48? We can, because we can come up with a rational converter, and we'll talk about a few different techniques here, but that's just an example where we might want to do that. Have you ever wanted to do that? PCs have typically used in their audio systems submultiples of the 44.1. 22.05 was one of the sampling rates, and then half of that, 11.025. And then after that, they just go down to 8 kilosamples per second, let's say, for telephony grade. But that's where some of those numbers came from in the PC audio system, and that's still supported to this day. So obviously we could use an analog technique. That's really off the table, but it would be, if we have a digital signal at 44.1, we'll just spit it back out as analog, and then we'll resample it at 48. That seems silly. If you wanted to go from 48 to 44.1, convert it to analog and resample it. So the whole idea of multi-rate processing is being able to change sampling rate, and initially it's just an integer reduction and an integer upsample, and then it will become the ratio of the two integers to get, you know, whatever we're looking for. So the first thing we look at here is downsampling, reducing the sampling rate by some factor, and that factor is going to be m. So we're going to downsample by m. So we're going to take, in our discrete time signal, which we're going to call our downsample signal, it's going to be every mth sample of the input. And it would be every m times t seconds of the original input out in the analog domain. But we're assuming, of course, at this point, we're assuming we don't have that original analog piece anymore. We only have the digital one. So how are we going to carry that out, and what does that do? So it's called a downsampler if it's just standing alone, and that's what it is in the toolbox I created for Python, called it's just called downsample. If you put a low-pass filter in front of it, it's typically called a decimator, but that's just sort of by terminology. So sometimes these get used interchangeable. The decimator, though, when I first learned that term, I thought, this sounds really interesting, and I think we have somebody from the Army in here. This is a military term, as it turns out. I read about it. You talked about rabbit holes. I went down a rabbit hole quite a long time ago reading about where did we get this from? So where do you think it came from? What does decimate mean?
Yeah, I haven't heard that term, but right now I'm assuming to decimate your opponent.
Yeah, decimate, though, but deci is 10, right?
Yeah.
So if you had 10 soldiers, if you decimated them, you'd only have one left.
10 to 1 ratio.
Yeah, exactly. That's what decimation is in my mind. So that's what we're talking about here. If we decimate by 10, we're only going to keep one of every 10 samples. If it's by 4, does all that make sense? So, but to me, decimate means more. It usually means doing something with a pre-filter. Downsample is just the raw, every 10th sample, no pre-filter. The reason why we'd want to have a pre-filter is that if we went back to the analog domain and we didn't properly process that signal to avoid aliasing, we might let aliasing creep in, and it's very easy to happen now with a downsampler if you don't pre-filter. So I generally think in libraries like in MATLAB and in Python, downsample is doing just this schematic, what I have here, but decimate would mean we're going to pre-filter to make sure that we don't commit a aliasing crime as a result of our downsampler. So if we go back to the analog domain, what we're going to do here is try to draw some connections, and it's going to be a little bit hand-wavy, but that's kind of that's the level I want to go to, and then have some rules of thumb to understand what's going on mathematically. So if we want to trace back to say what is the spectrum of our input signal X, back from the analog domain, it would be this equation that I have up right here. And then if I want to go and replace T by T prime, then in looking at the spectra, this T prime I would replace by MT. And we also see everything carries on through. So this is just what we were studying before from the continuous time domain, looking at the spectrum. with the downsampling. So we have replicas because x sub d of e to the j omega is going to be periodic. It's going to be replicas again, just like we had, but now we have omega over m times t is what's going to be going on, because that's what's happening in here in terms of the original frequency axis. We're dividing through by m times cap t as opposed to just t. So what the book talks about is re-indexing, and says that we want to relate x of e to the j omega to x sub d of e to the j omega, just re-index, saying that we're going to have m different replicas sort of interwoven with what the downsampled signal is. So what they come up with, and I don't have the proof of it, I'm just simply writing out what the results are. It's saying that it's going to be an amplitude shift of 1 over m as a result of downsampling. And if you want to have an easy way of remembering that, is if we have a whole bunch of samples and we only keep every mth sample, are we going to have more energy or less energy when we are the same? We're going to have less, right? So that's where the 1 over m comes from. And then in terms of the frequency axis, the key is we have omega has been replaced by omega over m. So that's where I circled this when I was studying the notes before class. I was saying omega now gets replaced by omega over m. So the way I like to think of this is as omega is moving up in frequency as omega, it's just moving, omega maps to itself omega, but if we're going to map omega to omega over m, it's going to roll out much slower. It's going to take more motion or more change in omega to roll out the same equivalent amount as it would without downsampling. So that's the omega over m idea. And I'm saying that rollout time, or how long it takes to cover the same amount of the omega axis when we're only plotting it as omega over m, that's going to pertain to the graphical solution we're going to be looking at here.
In that equation, is that pi just imaginary number?
No, that's just another. No.
Oh, that's the. I see.
That's this thing right here. Oops. Yeah. My pen is not working right at the moment, but I'll use this part of it. Yeah, it's that. I personally find this to be somewhat confusing, and I'm going to try to just navigate you away from trying to get this totally perfectly crystal clear. I want you to just get close enough to it that you can work the math in graphical form. It's all going to be there. It's just how you want to do it. And we know that when we think about what we're doing with sampling theory, what did sampling theory do? It made the spectra periodic. So whether we sample every n or every capital M times n, it's still going to be periodic. And if we're just getting samples every m sample, it's still going to be periodic, and it's going to be the same 2 pi periodicity that we had before. It's just as it relates back to the undecimated or undownsampled signal, it will have a different interpretation. So, and why am I being that way? It's because I've been involved with looking at this over many years, and I'm a wishful thinker. Like, I'd like to totally crystal clear understand it, and there's some times when I have to just be content with a certain degree of, maybe it's fuzziness. It's like I get it all, but it's hard to just keep it all loaded in your brain. It definitely works. I mean, I can model it on the computer and I can play with it there, and that's really what matters to me. So that's where some of these bullets exist. This was one way of trying to explain it. I just mentioned this one. It's always going to be 2 pi. And then probably the most important thing to recognize is that downsampling can cause great harm because aliasing possibility exists. why would you downsample in the first place, though? You either want to evoke a rate change by doing a small amount down and then back up again, or you just simply don't need all that data. You sample it at too high a rate, and for what you want to do with it after the fact is you feel comfortable sampling it at a reduced rate, or having less data. Is more data always better? I think we suffer from that, as a matter of fact, right? We get overloaded with too much data. So, and in a system, there might be a clock up front that captured data, and your task is to do something else, like measure the average power level or the signal levels, and you'd say, I'm going to decimate that down. I don't need that high update rate. So let's just go through an example, and then you'll be able to start understanding how this homework's going to work out. And it's still on the table till we leave, whether or not I'm going to make the due date Friday or next Tuesday. And I'll say it more later, but it doesn't really matter to me because you've got things to do, right? You now have a project to be working on, and you're never going to be without something to do pretty much right now. You got stuff to do for this class, and I know you've got other classes, so I'm not going to let you run out of things to work on. So start out with a triangle shape, and I'll maybe think about that helping some more, but I'm going to show you some of the Python stuff I have for this too that might help you visualize on the computer. But sketching is pretty important right now in this area, unless you can come up with something better. So sketch a triangle in the analog domain, then we know it replicates in the frequency domain, and then we'll look at what the downsampling does, and we'll do the upsampling and the rest of it. One of the things about coming up with some computer code in Python that I could throw at you is if it was too mysterious and too goofy, you wouldn't want to use it anyway because you wouldn't trust that it actually is right. I think drawing pictures sometimes is a better way to go because it's something that you can actually grab onto on a sheet of paper. I know that sounds, by today's standards, kind of like, do we have to do that? But what do you think? What do you do when you really need to do something more carefully? I resort to paper frequently just because I want to be able to draw a picture and just write it out. I mean, I don't know. Is anybody beyond the point where paper, they can work without paper all the time? I mean, drawing is just, I don't know. I think it's the way we were made to work. So I think you'll be happier. I'd rather you get this part of it first because it'll be easier and for some types of problems. So here we have our input. Now what we're going to do is we're going to say we're going to decimate by 2. So in this problem, it's sort of set up that we're going to do m is equal to 2. So this axis, this is in and out in the discrete time domain. So we have 2 omega axes, but notice that this is t prime and this is t. So we're going to go from the first line here is the input, and then when you see the 1 over mt, that means we've decimated by some, or downsampled by m. In this case, m is going to be equal to 2. So remember I said that this is going to happen. So what that tells us then is when we take a single point like right here, which is exactly at pi over 2, if we decimate or downsample by 2, that point is going to stretch out by a factor of 2 because it's going to take more motion in the omega axis to get it to the same value. It's going to roll out slower because you've got 2 in the denominator. Is that acceptable? I sort of think of it as a paint roller, and if you had 2 different diameters paint roller, one was a 1-unit diameter paint roller and you rolled out over one foot, And if you had a 2-inch diameter paint roller and you went to roll out the paint to go all the way around, you know, how many revolutions or whatever, you would have to do greater distance with a larger diameter roller. I don't know if that helps or not, but I sort of think about riding a bike or driving a car. I mean, the revolutions, big wheel, small wheel, and all that kind of stuff.
So for this example, if m was equal to 3, would there be aliasing?
There will be. That's the next example in the notes here. Something just hit me that it flipped through my brain and then it disappeared again. At any rate, so it stretches out by a factor of 2 because we're downsampling. So pi over 2, this point now stretches out to there. And this point here stretches out too, but it's really stretching out in a different, it's kind of hard to envision how that is. It's stretching out down to that same point. Can you see how that action is working there? So we put that together, and then we put it back on the analog frequency axis, big omega, and we see now that we had decent guard band between our spectral images, and now that we've downsampled by 2, we brought things closer together. We're right at the limit where we won't have aliasing. So we come up with a rule of thumb from this example, and that rule of thumb is to say that if we decimate by m, the bandwidth of the signal, or the protection that we need to provide pre-filtering, is going to be a bandwidth of pi over m. And that example you just went through just shows that, right? Pi over 2 we started at, and that becomes pi after we decimate by m, or in the case of 2. It worked that way. So this pi over m is sort of a magic number for downsampling. So that's, and just notice that that's missing there. So the anti-aliasing filter, or the protection filter, is a low-pass filter, and then in the terminology I've seen more frequently, this would be called a decimator because it has the filter and the downsampler together. Like I said, MATLAB and Python have those functions. I think it's easier initially to not play with those functions and just the downsampler, just something that just removes samples, and then think about the filtering action later. So here's an example where m is equal to 3. And this was your comment, John. This is exactly what you were saying. If it's going to start off at pi over 2, now it's going to go stretch out to 3 pi over 2, and this point here stretches down to there. And we have aliasing as a result of that. But what we can do to protect ourselves against aliasing in this picture is if we come along and protect the input with a cutoff frequency at pi over 3, and that's what's going on here. We'll take our input signal from up here, and we'll pass it through a pi over 3 cutoff. And now that point, when we decimate or downsample by 3, pi over 3 stretches out to right into there. So this is starting to make sense. If you're like me, drawing pictures is kind of fun. I mean, this makes it believable. And of course, it takes the amplitude hit too. It's 1/3 the amplitude. So when you're drawing these pictures, whether it be on an exam or homework, make sure you track the various aspects of this through. And generally what I like to do is I like to get a picture that covers -2 pi to +2 pi. I mean, technically minus to plus pi is good enough, but I think minus 2 pi to plus 2 pi kind of gets you a better perspective on the whole thing. Let's just take a quick look at what I did in Python. So in Python, I said, let's synthesize a waveform that has a triangular shape to it, is what I did. So I said, we know a sinc function gives us a rectangle in the frequency domain. How about a triangle would be a sinc squared? So what I do down here is I end up doing sinc squared. So there's the sinc squared function plotted out, and then here, remember how I told you weeks ago you could use the freq z function and put the time domain variable in there, and for the b vector, leave the a vector as 1, and then this will approximate the Fourier transform of that sequence. So do that. Don't plot it on a log scale because that will make it see the imperfections, but on a linear scale, looks pretty good, doesn't it? I mean, it looks pretty much like a triangle. I used a certain length there to get that, and I can change, the scaling factor if I want to. Here the cutoff frequency is 0.25, so suppose I made that 0.33. Or what number do you want me to pick? What's a better number? 0.5, okay. Cool, right? Okay. Put it back to 0.25 right here, and then I'm going to downsample by m is equal to 2. So what we expect, right? And now I put in 3, just like we did in the hand-drawn stuff. And it doesn't look quite so beautiful anymore because what we're seeing is the superposition of the alias terms are summing in on top of it. So we're seeing, back over in here, we should see something more or less along the lines of what we see here, and we're going to see this fill in, right? So that's where Python doesn't do such a great job. In modeling, if I was to model this, sketch this out, the alias, that would be the superposition here. That would step up twice. And then here it would be the same. So I think it's more or less just going to fill in as a constant across there. Python didn't quite make it look so nice, but I want you to do something like this when you're drawing pictures because this is more logical, right? Just to draw a picture. So, and you do have some homework problems where you have to do things like this, so just do it. I mean, it's better than trying to make the computer do something better than what I think our brains are better at, drawing pictures on the page, to get a theoretical handle on what's going on. So the next thing is increase by sampling factor, and most textbooks, or this textbook likes to use L, upsample by L. So L is called the upsampler, or in the book it's also called an expander, or sampling rate expander. Upsample I like because it's the complement to downsample, up or down. So the upsampler does this. It inserts zeros in between the original inputs because it's going to upsample and it's going to leave space for later interpolation to make it look like it's a higher rate signal. So this is what the textbook has, and this actually is beautiful. the upsampler is easier to understand mathematically than the downsampler, or at least in my view it is. If we plug this delta function into the upsample operation and take the Fourier transform of it, it will pop out with what we would have liked to have seen for the downsampler, but it has extra terms, m extra terms in the downsampler, but in the upsampler it does this. It puts, as I sketched out here, omega times L. So now it's rolling out faster. So it's like the wheel is smaller when you upsample, and it repeats over and over again multiple times in a 2 pi interval is what it's going to do. So it creates more copies rather than less copies. I'm saying that, I feel comfortable with it, and I go back to that. You're going to have to get comfortable with it. You're going to have to make sure you don't get them in reverse somehow or another. Slower, faster, more copies, less copies. So if we upsample by a factor of 2, suppose we start off with a signal which is the triangle we have right here, then we upsample by a factor of 2, and it's going to replicate copies. So notice what's going on here. This is, oops, got excited and bumped my mouse grabbing my pencil, but this is L is equal to 2 in this example. So it's pi, and now it rolls out twice as fast rather than half as fast. So this point here is now going to map to right there. So that whole triangle centered on 0 is scrunched up, and then it doesn't try to take this copy here and scrunch it necessarily in here. It's just going to put in extra copies as a result of stuffing the 0. So there's another copy there, and then there's another copy, and then there's the next period here. So I have a rule of thumb or an understanding for doing upsampling that says if we're upsampling by a factor of 2 and we plot from say 0 to 2 pi, I have the principal copy, the copy from L is equal to 2 is here, so there's 2 of them, and then we start over right here. So if we're going to do L is equal to 3, which I think is the next example, we'll have 1, a copy, and then another copy, and then we'll start over again. So I can count the number of copies in there by not counting the copy at 2 pi. How do we get back the upsampled signal without the image? So this is we have to use an interpolation filter. So the interpolation filter is going to come along with a cutoff frequency of pi over L, and I don't, where did I write that? I didn't write it anywhere yet, but to clear off the image. And you can think of the action in the time domain is when you clear off that image, you now connect the dots. Rather than having 0 dots, you fill them in with the appropriate interpolated values. Does that make sense? Okay. So the ideal filter is the sync function. It's going to interpolate perfectly, and it has to have its cutoff frequency again at pi over L. Before we look at another example, this is a nice kind of a cool thing to think about too, is what is a perfect interpolating filter. I'm remembering back to high school or middle school or something. Somewhere in algebra, don't you learn about linear interpolation? You still do that in school? Because I don't know. I did it, but I don't know. Can you think back? Like you have some data and you want to interpolate.
Definitely sounds familiar, but I don't remember what we did.
Where you did it, or?
I think we did it, but
Maybe in physics or just in math class?
I think just in that.
Yeah. Well, you know how to linearly interpolate, though, data points. If you've got raw data and you want to put another point in there, you just take the 2 points, and then you find out the slope, and then you can use either the first point or the second point, and then know where that point in the middle has to go. Linear interpolation is what it's called, right? So it's based on the slope. So the filter that does that is a triangle-shaped impulse response.
So going back a little bit, T prime, why do we care about T prime? And why is 1 over T prime the amplitude of the analog signal?
It's because way back in the beginning of the chapter from the Fourier transform pair, we had it. So if I can get there. It's way, way up here. That's it right there. Comes from the...
But that's
Yeah, T prime is just in the new domain, though, right? It's either smaller or bigger.
okay.
But to answer your question, why do we have T prime and why do we care about it? It's just kind of like a crutch. It's a stepping stone to say we want to take the input signal, draw it backwards to the analog domain, and then we want to take the analog output or the digital output signal, draw it back to the analog domain, just to say that we could have started in the analog domain and done it right the first time, sampled twice as fast or half as fast. So just kind of like a stepping stone. But it's good to have that, though, to just think about it, because it helps you think of the sort of the reality of the matter. I like it myself, but it's not vital. I mean, it's not, it's just as a matter of fact is what it is. But the way the book is written is kind of like you sample at either twice as fast or half as fast, and now you want to change that, and you've got the data, so how are you going to do that? Because you can't go back to the lab and take data again. So went too far here.
So it's sort of like that energy thing that you were talking about earlier?
Joules.
Whereas, like, if you, like, this T comes from, if you're sampling, there's going to be repetition, so it decreases by T.
In the downsampler, yeah. In the upsampler, there is no change in the energy because you're not adding any samples. In the upsampler, it just adds 0 samples.
Okay.
So there's no amplitude shift there, and that's, we just came through that because I was right over here. That. Whereas the downsampler has, and this side of it had the M in there. So it's asymmetrical. Sorry. But you think about the mathematics of it, and it's the way the interpolator or the upsampler doesn't have an interpolator, so it does the dumb thing. It puts a 0 in because it doesn't know what it should be unless you want to provide an algorithm to estimate that. And that's what we're talking about now. Is I'm hardened by teaching this so much that I just accept it, but you're new, so you have the right to be what all engineers are supposed to be, skeptical, right? So I'm fine with it. So here's the triangular impulse response shape, and this is shown as a non-causal filter, but it gets the idea across that if we use this shape over here, H lin, make it a triangle that lasts L plus and minus L samples with zeros at the edges, actually. So 5 is here over to there. That triangle with the ends of 0 will take, and this to me is extremely gratifying the fact that if this is the upsampled value or expanded value, the zeros are stuffed in there, and that triangle will take these data points and it will make the perfect linear interpolant. Now, that's very gratifying. It doesn't work very well, though. I mean, it looks good in the time domain, but if you look at it in the frequency domain, look at the Fourier transform of that triangular shaped impulse response. It's a sinc squared function, or it's an alias sinc squared function. And the problem is it doesn't cut off at pi over 5 for this L is equal to 5 example. So it has leakage in it, and it rounds off in the passband. But it's a poor man's interpolator, so I guess maybe that says that linear interpolation that you learned about a long time ago was kind of hackish. It's good, but not that good. But of course, if you are upsampling, well, I don't know. I have an example. I did an example of it in the WX Maxima stuff that I wrote up at the end of the summer and published on GitHub, of where I go through that just as an example, and you will experience it in problem 2 of the project, where you will see that you will get some artifacts coming through, some aliased artifacts will come through with that sort of interpolator, the linear interpolator. So I guess I don't have the example in here that I thought, but let's go look at Python. So let me reset this back to 2. So do the same thing with upsampling. Use 0.25 and upsample by a factor of 2. And now we see the images in there, so let's upsample by a factor of 4. Well, let's do 3. So remember I said not including the first period, there's 1, there's 2, as you go from 0 to 1 would be 2 pi, right? Because I'm normalizing by 2 pi. So let's see if when I plug in 3, it's not looking so good right now in terms of the approximation, but 1, 2, 3, and then it repeats again, and 4 should be the same thing. So it's what we expect it to happen, right? And our job has to be, if we're going to upsample by 4, is we have to filter out these spectral images because they're bad. There are leakage. But hey, we have them because of the zeros that got stuffed in there. This actually relates back to that impulse train that I had in chapter 2 in the appendix, to say you get some periodic thing going on when you put zeros in. So here I design a better interpolation filter. It looks like, I haven't played with this. Try it really fast, see if it works. Yeah. I did a Kaiser because last week I hadn't updated my Python. I had in the notebook originally the Remez, but I had to upgrade my Python. Remember we talked about that weeks and weeks ago, and I forgot what I had to do, so I had to go into the command window and upgrade my Python. So let's see if I can find it. So I had to go to Conda when I was pointing not to the base, but to the virtual environment for Python 3.1.3, and I had to say Conda install SciPy equals 1.16.2 if you installed it originally with Conda, and then it works. So there's, let me finish this and I'll get your question. There's whichever filter we want to do, but now I'll look at what it's doing. This is with, I think I have to switch this back to 2. So now I'm going to use a filter. I'm going to do L filter. And then I'm going to Fourier transform that, and image is gone, right? We'd have to make the filter narrower if we upsampled by a factor of 4, so that's why that didn't look good the first time through. So
what would it look, what would the frequency response look like without interpolation? What does it look a lot worse?
the spectrum is going to be filled with all those images.
Okay.
Yeah, they're junk. I mean, if you're building a radio transmitter, you're broadcasting all kinds of stuff into, radiating all kinds of stuff, and you just have to clear it off. Have to design a filter, and there's a filter that we'll talk about that's also in the toolbox, which is a quick first cut, and then you can fine-tune it later if you've got a lot of sampling rate, a larger upsampling factor. It's called a cascaded integrator comb structure, or a CIC filter. That's been a second project years ago in this class too. It's used quite a bit to get at it faster without building a high order interpolation filter. Okay, you can see I've got in the notebook here discussion on the two projects. We'll get back to that later, but notice I think we're right on track because we're about ready to push through some examples, and then we'll get into probability and random variables before too long. So we're pretty good. But okay, now we can take what we've learned for the downsampler and the upsampler, combine them together to get the rational rate change. So this is pretty nice the way this works out. You want to put the interpolator first because it needs to have the filter at the back end. You put the decimator second because it needs it at the front end, and then you can combine those by choosing the minimum cutoff, pi over L, pi over M, and then you've got the rational rate changer, like to go from 44.1 to 48 or vice versa. Large ratio of integers is what would be involved there, which is not necessarily a good thing to do. So, running out of time. I've got several nice examples. Do you want to see an old-fashioned audio technology example, or do you want to see computationally an example that's not in the notes, but I have it here? I'll go through it no matter what. So do you want to see technology through the ages, or do you want to be motivated that multi-rate does really, really work and it's computationally practical if you do it right? You care? Okay, sure. So this is from a magazine that went out of publication a long time ago, but it had a nice quickie tutorial in there one time, so I decided to just pull it out. But you go on the internet, people write tutorials too. So here's upsampling in the time domain. We stuff in the zeros, we have and then we filter it to interpolate. In the frequency domain, when we upsample, we see the images, and then the filter removes them. This is just a really kind of like a stick diagram, just reviewing that. And here's going the opposite direction. Here's decimating. Original signal, we filter it to make sure we don't have high frequency component. It's not super obvious in the picture, but we downsample it and then get our downsampled output, but in the frequency domain, we have some frequency component here that can't be present due to aliasing, so the filter chops that off, and then we get, the stretched out spectrum because of the downsampling. Suppose you want to do quite a bit of downsampling. In this example of multi-rate processing, they want to do a factor of 12. For that, let's write this down here. Suppose you have to convert from 44.1 to 48. You have to keep it in integer terms, and that's the ratio you have to go through. You have to go up by 480 and down by 441 to go to the higher rate, or you have to go the opposite, flip it over to go the opposite direction. So 12 is still a pretty small decimation or upsampling factor, but it just gives you the idea of what you can do. So if you do it all at once, build a high order low pass filter, it says there in the notes we want to get a band reject of 60 dB in the aliased components with a 0.1 dB ripple bandwidth. You need a 388 order low pass filter, FIR filter. And if you're running at an input data rate of 1 megasample per second, and you're going to upsample to 12 megasamples per second, the computation rate to do that 388 tap filter is going to be 4,565 mega instructions per second, or MIPS. And the practical matter is you don't want to do that. That's just like lifting too much weight. You can't do that. So you can do multi-stage, and the multi-stage can do, it breaks up 12 into 3 smaller integers. So in this case, it's 2, 2, and 3 to get 12. So you do a factor of 2, and you end up with a 121 tap filter. You do a factor of 2 again. I'm reading this as 121. That says 17 and 13. I guess I'm not seeing, this isn't adding up to me right now, because I would think this would be similar. At any rate, though, the bottom line there is what really matters. It says if we do multi-stage upsampling, I think that 121, it doesn't seem right to me. I don't know. I'm not going to argue with it right now, but it says down below here that if you build this up as three upsamplers in cascade of lower rate each, it's only 1.035 mega instructions per second versus 4.5. So that's a fairly good savings. But the thing that is definitely the most popular technique today is polyphase filtering. So if you go with polyphase filtering, and we'll talk about that briefly next week, you take the original 388 tap FIR filter and you decimate it into 12 subband filters. So you take that long 388 tap filter. This used to be project problem number 3 to do something with polyphase, because I was trying to sell you on the idea of polyphase. So you're taking a different phase of the impulse response you're taking like the long filter and you take every 12th sample, but you shift it over, so each one of these filters here is a different filter extracted from the long filter by just phasing it a different tap length over. You have 33 taps per filter approximately, with 12 of them. You're running at 1 megasample per second, 33 filters, 33 taps and 12 filters, 396 MIPS. So this is definitely very attractive looking in terms of being more efficient. And it turns out you can do the polyphase in the opposite direction too, so you can use it for not only upsampling, you can use it for downsampling by running the polyphase filters. Why did I add this in? The book added it in this edition, but places that I've worked just do polyphase automatically, and ASIC people do polyphase stuff too. It's not something that you really have homework problems on, though. It's just something that I want you to be aware of. And so this example I just went through was to try to drive home the fact that polyphase makes sense. Brute force is not acceptable. You have to be more efficient. Now, if you're modeling something on the computer, though, whether it's polyphase or not, it's still going to get the same effect. So I will not necessarily do polyphase, but there are libraries out there for polyphase that people have written. So homework's not due on Friday. But, you know, you got to work on it, so just work hard on it. I want you to just simmer on it, and if you'd rather work on the project some, I want you to be working in parallel. And what do I do when I'm working in parallel? I like having a break. My brain gets wiped out focusing on one thing too much, and I just have to switch. If you switch too rapidly, you're very inefficient, but if you know you got to get both these things done, I look at it as I'm taking a train and moving it down the tracks. I've got to take this one and drag it all the way down and get exhausted. I take this one, drag it all the way down, get it exhausted. I'll just kind of take turns, you know, pushing, pulling my load down. And you do that in your classes anyway, right? You switch which nights you work on which class, whatever, so. But you're going to get some efficiency because you're going to see certain things that are going to pay off, and you can pick and choose perhaps what you want to do. I did put the hints up last week. The hints are pretty valuable for the homework, without a doubt. Drawing the pictures is what you want to do, and you might draw the pictures. You might also be crazy like me. I have my engineering pad that I'll draw pictures on, and I will draw page 1, I'll work it down, say, I don't know what I want to do next. I'll go do something else for a while, but I'm still working. I'll come back and I'll say, let me do a take 2. I'll flip over to page 2 and start reworking it or pushing it further, but I will write scribbly notes out on different problems that I'm working on to kind of let something simmer for a while. For me, it's very important to be able to let something simmer, because if you don't do that, you kind of get really burned out feeling. And I know if you're a cook, I don't know if you're a cook or not, but my wife likes to prep things and make things partially and then finish something off, so it's not done till it's done. So that's how I did this project. I worked on it and set it aside and maybe did something else for a while, because I get too tired out, daunted. I'm stopping.